Our speaker tonight is Professor Gary Haller of Yale University. Gary got his PhD from Northwestern University. He's held a number of positions and traveled around the world. He has worked his way up. He's held numerous offices in the Catalysis Society. He's currently president of that organization, and seeing that we're hosting the 12th meeting, he's here checking this out. Make sure the arrangements are up to snuff. And he's going to talk tonight about non-acidic reforming catalyst metal support interactions.
Thanks, Jim. Well, it's a pleasure here to be here, and I am not checking you out. To give you a talk. The first overhead has a somewhat different title than the one that Jim gave, but that's just because I didn't take time to write down a new one. But it does outline what I'd like to do. Is there a pointer? Maybe I can just use. But I want to. This is all right. I'll just do it here. Okay. Yeah, that's great. So I want to talk a little, break it into three parts. I'm going to talk a little bit about non-acidic reforming, in particular platinum zeolites, which you probably have all heard about. And then I wanted to actually talk about our work where we tried to probe the nature of the platinum zeolites by both chemisorption and catalysis, chemical probes, and by physical probes. And mostly the physical probes I'm going to talk about today will be X-ray absorption Zane's, the X-ray absorption near-edge structure analysis, and XAPS, X-ray absorption fine structure analysis of the platinum particles in the metal zeolite. We've done some NMR and some other physical characterizations. I talked about NMR earlier today, and I'm not going to do that today, this evening. Of course, conventional catalytic reforming is bifunctional. It involves, if we look at this particular reaction, which is the test reaction for which platinum L is best, the conversion of normal hexane into benzene, there's a dehydrogenation and hydrogenation, there's a dehydrogenation and sometimes hydrogenation process, but in this particular case, dehydrogenation and dehydrogenation process, that occurs on the metal function, and then on the acid component, which is normally, say, chlorinated alumina or some other form of alumina that's made acidic, we go through an acid catalyzed function. While on the platinum L, there's pretty good evidence that there's some sort of direct reaction that's normal hexane to benzene. At least it's not bifunctional in the normal sense. Now, some of the test reactions that we've used to try to understand, to probe the nature of the platinum void interactions does suggest that there may be bifunctionality, but bifunctionality of a different kind, not involving the acid function of the void. I'll come to that in a moment. The initial work was done in France by Bernard, and on here I'm not going to go through any of this, and it was published in this 5th International Conference on Zeolites in 1980, though the work was done in the 70s. There are sort of just 3 points that I want to make from here. We won't look into this in any detail, but a variety of zeolites have been used with platinum, and they have been compared to platinum monoacidic alumina and a platinum bimetallic catalyst. One presumes platinum rhenium, though that's not specified. And the point is that all of those have much less selectivity than the platinum L for this reaction, normal hexane into benzene. Now, there's a little cheating going on here because it turns out that the selectivity is highly dependent on the conversion, and the selectivity only gets very high at high conversions, and you can see that these are not all at the same conversion. But still, even when you put them on the same, normalized into the same conversion, platinum L wins. Now, the evidence that it is not bifunctional, or at least it doesn't involve the acidic function, is primarily of two kinds. Actually, there are several circumstantial bits of evidence, but in the original work of Bernard, they were two kinds. One was that it was the potassium L, and you could decatenate it, i.e. exchange the potassium for ammonia, and then convert that to proton form. And as you do that, to a greater extent, the selectivity is decreased rather than increased. So if you add acidity to the support, you lose selectivity for hexane to benzene rather than gaining it. Perhaps a more convincing bit of evidence that it's not the normal mechanism is that, as you recall, for normal reforming, you go through ring closure to in the case of in hexane, to a methylpentane, and then ring expansion on the acid function. So one would have thought that if acid function was important to get to benzene, if you started with methyl cyclopentane as the reactant, you would get more benzene than if you started with normal hexane. And in fact, you don't. The selectivity of N-hexane to benzene is always higher than it is if you start with methylcyclopentane. Moreover, there's some evidence that in fact the way you get from methylcyclopentane to benzene is to first go back to normal hexane and then benzene. So that there's a lot of evidence that says that platinum L is very different from a conventional catalyst, and the thought is that it is probably monofunctional. And yet, L does seem to be unique. You can try other zeolites that you might think would be similar, and they seem not to be. And so the question is, what's different about L? Well, it's different in a lot of ways if you compare it to something like Y, because that's three-dimensional channels, and L is a set of parallel channels, though the size of the openings and cavity are not substantially different. But another way it probably is different is that it appears to be more basic. And this is not evidence for this, but it's an interpretation of this taken from a recent review article of Jules Bravo, where what is being looked at here is the calculated potential energy between the protonated form of the SiO Al and the deprotonated form. The deprotonated form is here, and here's the protonated form as a function of the silicon-oxygen aluminum bond angle. And what one finds is that the potential, the energy it takes to deprotonate, to release the proton, is much higher if you have angles that are around 130 than it is if you spread that angle out towards 180. And then on top of that, I plotted the range of angles in three sets of zeolites, ZSM5, Y, and L. And as I was saying earlier today, it's really hard to interpret this, use this calculation to decide what the acidity of any of these zeolites are because of the range of angles you have. You only have, I think, 4 in the case of Y zeolite, but if you go over to the ZSM5, there's some 27 different silicon-oxygen aluminum bond angles, and so the question is, where's the aluminum and which of those are the acid sites that are accessible, and so which are the ones that I should put on this potential energy diagram to decide whether ZSM5 is acidic or not. In any case, the sort of feeling that the order of acidity ought to more or less go in this direction would be consistent with the idea that has developed that L zeolite, the thing that might be unique about L zeolite as a support is the fact that it is basic. And in fact, it was that idea that first caught my attention because we had been for some time looking at metal support interactions. We had particularly been interested in the rhodium on TiO2 system. And it seemed to me that the metal zeolite was possible, another example of metal oxide interaction, and it seemed to have some advantages over the others that we've been looking at, because the idea was that you could fill a core with a particle, and therefore you might have a more uniform particle size, that if there was interaction between metal oxide, you could sort of encase the particle so that you would have a much larger fraction of the metal particle interacting with the oxide, so you might see bigger metal support interaction. And for a variety of reasons, I had thought that that would be an alternative explanation for why L was important in this hexane benzene conversion. Now, and I say important because there was another thesis that was coming out of First is Exxon, and then Eric de Ron from Belgium, which was that it was primarily a geometric effect. Here's some one plot from Haus and Steger work. What's being plotted here is what they call a selectivity parameter. It's the weight percent of benzene over benzene plus the cracking product C2 to T5 against what they call the terminal cracking index. The terminal cracking in hexane is the reactant. Terminal cracking index is the sum of the cracking products, hydrogenolysis products that are pentane, or the sum that are butanes. It's some measure of the rate at which you just crack off the N carbon to make pentane versus cracking somewhere in between. Down here you have platinum on silica, and here you have a whole range of different potassium L-zeolite supports. And there's no question that the selectivity goes up when this terminal cracking index goes up. But the question is it cause and effect, or are they just two effects that are parallel with each other? The idea that they had was that normal hexane sort of goes down these parallel channels and has a preferential end-on collision with the platinum, and then you get 1-6 rings collision. Now the problem with that is if you look at normal hexane and you look at its conformers, it can easily ball up and just move down the channel any way it wants. There's no reason why it should hit end-on. And so that doesn't look very convincing. Eric de Waalm had another version of this, which he called it pre-orientation, of the sort of molecule sort of nest in the zeolite and starts to curl around on itself. That wasn't very convincing either. But we did look at this channeling effect, and we did it with another molecule where the conformation, we, in this case, is an extended we, a former student of mine who's working on this project with me, was actually done in his laboratory, Daniel Osco. The idea was that you choose a molecule where the conformation ought to be one that is sort of pretty well defined, i.e. methylcyclopentane, and now look at the selectivity between the possible hydrogenolysis products. It can crack here or here and go to hexane, or here and go to 3-methylpentane, or here or here and go to 2-methylpentane. And the idea would be that you expect a selectivity change when you conform it to go down the channel, because this one you might would have thought energetically would either approach the platinum particle blocking the pore, methyl end first, or this end first. And so the prediction would be if there's a geometric effect, you'll shift selectivity away from 2-methylpentane towards N-hexane or towards 3-methylpentane. And in fact, that more or less works. If you look at, these are results of platinum on silica, and I guess this is the 2-methylpentane, and this is hexane and 3-methyl, so the prediction would be if there's a geometric effect, you expect to increase the, say, hexane at the expense of 2-methylpentane. And in fact, something like that actually happens. When you go to the L-zeolite, you do see a shift towards the N-hexane and 3-methylpentane at the expense of 2-methylpentane. So it does seem to me that there is some component, there may be some component of this geometric effect here, but I don't think it's the primary one that's involved in causing the normal hexane to benzene reaction. Now, another thing that I can say before I get around to talking about the details of what we tried to do is that after all this work, well, you're probably quite aware that a lot of effort is going on in this area now, right? The first people on the bandwagon was Chevron, and then along came Exxon. That I don't know what their current count is, but I did a literature search a few months ago, and they had 32 patents in this area. UOP is active, and probably several other people that I don't know. But Chevron got several patents, and one would ask, given all that Bernard did and the way they patented and published it, what did Chevron add? Well, what Chevron did add, I guess, was an elaboration on this question of non-acidity and how you could make the support even more non-acidic. And their measure of non-acidity was the absorption of pyridine. And here, as a function, and changing the cation from potassium to these alkaline earths. And here's the acidity when you calcine at low temperature: magnesium, calcium, strontium, and barium. And then if you calcine at 866 and exchange with barium, there is, by pyridine absorption, no measurable acidity. Why is that? Because if you put alkaline earths in most zeolites, they may neutralize the acidity of the anion host, but then they hydrolyze water and they add a proton back and they create acidity. Well, if you look at the structure, what's happening is that there are these normal channels, but then there are these small lock cages off the main root, as it were, cancrinite cages. And in fact, when you calcine at this higher temperature, the barium moves into these lock cages. So it may well hydrolyze water and make protons, but it puts them either there's not room to get the hydrocarbon in there, or they're not accessible. In other words, it doesn't put the protons along the channel where you can get a pyridine, and so that's probably the reason it's non-acidic. So that was Chevron's, I guess, basis for their patent. It certainly was a modest, maybe not a modest addition to our understanding that you could make it even less acid, make even more bases, and in fact, it does make a better catalyst. Another point to be made is that what this catalyst is really good at is normal hexane to benzene. This is the relative aromatic reduction as a function of carbon number. And its selectivity relative to conventional platinum rhenium sulfide treated in the proper way, one must assume, since Chevron did this, falls off as you go to higher carbon numbers. So what's really unique about it is hexane to benzene. It sort of loses its uniqueness when you go to higher hydrocarbons. Now, I'm not going to have time to develop another line of argument about why the geometric effect is important. That means that I didn't get around to making the view graphs for the articles. But there are at least two examples in literature where similar kind of behavior has been noted. There was some work done almost a decade ago by British Petroleum, where they supported platinum on carbon and promoted it with sodium. And if you look at those results, they look very much like platinum and L-zeolite. In other words, maybe what's unique here is the basic support, not the zeolite at all. Though in a personal communication with Richard Joyner, he tells me that it's different from L-zeolite, because if you think that you can make, as this one does, when you go to heptane, you can get a high yield of toluene. When you take the platinum on carbon promoted with sodium and you put in heptane, you still get benzene. It lops off the alkyl side chain, so it's different in that respect. The other work is more recent. It's work by not Mark Davis, his brother Robert Davis, and Eric Deron, platinum supported on alumina stabilized magnesium, which is also a very basic support. And that looks identically, at least in the results that they have submitted to the journal Analysis, but it's not yet published, that looks identically like the L-zeolite. So there's lots of reasons to think that maybe what is unique here is a basic support, not that it happens to be a zeolite. Anyway, this is the avenue of research that we were trying to follow, and some work, again, in France has suggested, as kind of obvious, that one might probe that by looking at the shift in the carbon monoxide absorption. The idea would be that one might expect that if you had a basic support and you, instead of the basic support sort of transferred electron charge to the platinum particle would be electron rich. You would get more back bonding to the chemisorped CO. That would then cause frequency shifts in the carbon-oxygen stretching frequency towards lower wave numbers. And if you look at things where you're now going magnesium, calcium, and barium, in fact, you do see such shifts in the linear. I'm not quite sure what's happening down the grid. But this is at room temperature where you're at full coverage and there are lots of dipole interactions, and it's not at all clear that there aren't coverage effects that dominate the effects there. So what we wanted to do is try to find temperature. Coverage was rather low, but still measurable. And so now I'm showing you the IR of CO as a function of different desorption temperatures. This is room temperature, and then at 383, 493, and 593. So we chose to compare them now at 493, where there's still quite a significant coverage of CO and several different states moving to low frequency, but certainly the coverage is decreased enough that one might expect that dipole-dipole coupling shouldn't interfere with determining whether there are shifts to low frequency that conceivably could be interpreted as the result of the platinum being electron-rich. And again, that seems to qualitatively fit that picture, that as we go to what is supposed to be the more basic support, L ion exchange. I really should call these potassium barium L and calcium, because only about, I believe it is, a fourth of the potassium is ion exchangeable. Only those potassiums along the main channel are ion exchangeable. And if you then calcine at a high temperature, you move the alkaline earth into these canconite cages and put potassium back. And so in fact, it has a lot of residual potassium in it. But as you go from the magnesium to the barium, well, there's not much function of change in this peak at the highest frequency, but this peak moves to lower frequency, as does this one, and actually it seems to be a fairly low frequency peak that develops on the barium that's not there for the magnesium calcium. So there's some modest evidence that these are very basic supports. I sort of discounted all of that because when I looked more carefully at these, by looking at a reaction of CO, I really believe that maybe there's another interpretation of what CO is doing. Here what I'm doing is bracketing the CO hydrogenation frequencies on these three catalysts by what are less or non-interacting, more or less non-interacting supports, and what are supposed to be very interacting supports, platinum on TiO2, either reduced at low or high temperatures. As you all know, these have very high methanation activities relative to something like silica, which is less than alumina, which is about the same as the silica alumina. And what you find is these basic supports fall somewhere in between these two. And I had always believed that, in fact, in addition to the TiOX covering the platinum particle, we had XBS, and we have near-edge evidence that suggests that there is electron transfer from the support to the platinum. And so to the extent that that might explain these higher rates, then treating this as a basic support where there's electron transfer from the support to the platinum might fit into this same scheme. And so when I first saw this, I was rather encouraged that we had another bit of circumstantial evidence that there's a basic support with electron transfer to the metal particle. Why am I not of the same view today? Well, the recent work by John Robbins at Exxon and of John Faulkner at Colorado has now suggested strongly that the CO hydrogenation is bifunctional. It's bifunctional, not bifunctional that you have a metal acid property, but you have a metal and more basic property, and that the CO is moving off of the metal and forming a methoxy intermediate. And what is being shown here is the relative amount of the methoxy intermediate, which is being hydrogenated to methane, and the CO absorbed on platinum, which is being hydrogenated to methane, in temperature program reaction experiments. And what's changing these is the temperature at which you reduce the catalyst, but as you reduce to higher and higher temperature, in this case the higher temperature 723, you dehydroxylate the alumina, and you make a site to move the CO off of the metal and out here on the alumina. And so the more dehydroxylated the alumina is, the more you make of this species. And what's interesting is that you hydrogenate this species, which is identified and seen in the infrared, at a lower temperature than you hydrogenate this species, which originates from CO chemical metal. And so that suggests that, in fact, this route might compete with this route. And so I actually think now probably the better way of looking at both the platinum on the TiO2 and the platinum on the L zeolites is a different kind of bifunctional reaction, and it isn't telling us anything about electron transfer. So wipe all of that off the slate, and let's go try something else. Well, the next thing, actually, something that we tried earlier was competitive hydrogenation of benzene and toluene. Now, the idea there is that it's a zero-order reaction, and so the particle is completely covered with the aromatic, and the ionization potential of benzene and toluene differ by about 1 volt. The toluene is a better electron donor than the benzene. And so if I measure the absorption equilibrium constants of benzene and toluene in competition, then as I go to a support which donates more electrons, the benzene will be better able to compete with toluene than it is in the more acidic support. So that's the prediction. It assumes, of course, that the way benzene is absorbing on the metal is pi ring down, not phenyl, right? But there's good independent evidence that that's a good assumption. This is some what is called NEXAPS here, near edge X-ray absorption fine structure. It's angular dependent X-ray photo emission, and from that one can determine the orientation of the benzene ring, because you can look at these transitions, which are 1s to pi and 1s to sigma, and if the electric field is in the direction of the orbital, in this case if the orbital is carbon-hydrogen one, then the electric field is at right angles to the direction of propagation, which is in this direction. And so we expect lots of excitation in the 1s to sigma if the benzene is parallel to the surface, which is what we see here. On the other hand, if we come in the glazing incidence, so that the electric field now is in this direction, so that it's from the 1s out to the pi, we expect a lot of intensity in the 1s to pi and not much here. And in fact, that's what you see. So this is direct evidence that the benzene does absorb with the pi ring parallel to the metal surface. That's important because, in fact, it's only in that orientation that the comparison or the competition between benzene and toluene really would have this acidity measure that we're after. Okay. Now what do we do? Well, we measure the absorption equilibrium constant, but we want to do it under reaction conditions, and so we measure it kinetically. The rate of benzene hydrogenation in a Langmuir form is a rate constant times the Langmuir absorption expression, which is just the equilibrium absorption constant for benzene times its partial pressure over 1 plus that. And since this product of pressure and absorption equilibrium constant is very large compared to 1, those essentially cancel, and it's zero order. It's zero order at low temperature. So that the rate of benzene is just the rate constant, rate of benzene hydrogenation neat. Now put in some toluene. Well, everything's the same now, but we have another term which represents the equilibrium absorption constant and partial pressure of toluene, and everything else is the same. Again, the 1 is small compared to that, so that we drop that and we get this expression. And we define Kt over B as being the ratio of the absorption equilibrium constant of toluene to benzene, and we take the ratio of these two, the ratio of the benzene hydrogenation neat to the benzene hydrogenation in the presence of toluene. And if you just do your algebra on that, you get the ratio of the rates of benzene hydrogenation should be a linear function of the partial pressures of toluene to benzene. It should have an intercept of 1, and the slope should be the ratio of the absorption equilibrium constant. And if you do that, you get nice straight lines. This is the ratio of the benzene hydrogenation rate pure to the competitive hydrogenation of benzene against the ratio of partial pressures. You get a nice straight line, which has an intercept of 1. And so we take the slope of that line as the absorption equilibrium constant. So we're measuring the competitive absorption equilibrium constant under reaction conditions. And now this really does look like that the more basic supports are causing the platinum to be electron rich. And I can't think of any way of debunking this, but you might help me out there. This does seem to be evidence that that's the case, that it changes systematically, and as you get to a more basic support, where electrons might be donated to platinum, then benzene, which has the higher ionization, which actually, let's say, toluene, which is the more electron donating, and therefore benzene can't compete with it, except when you put large charge on platinum. You would expect this ratio to decrease as you go towards a more basic support. These are our numbers, where our reference is silica, which we take to be rather neutral. And here we have an H potassium L, which is somewhat acid. And then these are actually numbers from literature, where this is a comparison of our number versus the one that has been measured by Galazzo and colleagues. And they'd also done it on some very acid supports. And there's a nice progression over roughly an order of magnitude change in that, which says that there is some correlation between acidity, at least as probed by this competitive absorption, and the acidity of the support. Well, one other thing which should have been obvious here, another advantage, or at least thought, was that benzene hydrogenation was the reverse of the last step in the reaction we're interested in. It was hexane to benzene resorption, right? We're looking at the reverse of that. So while it's not in the same temperature regime, but at least it is the reverse of the real reaction that we're trying to probe the metal support interaction for. Okay, now that's sort of where we are in the probing of the interaction with chemisorption. I haven't actually told you about chemisorption, but catalytic reactions. There are a couple more that we're doing. Neopentane is one that we are just now looking at. Some recent work by Zockler and his colleagues suggests that if you donate electrons, in his case palladium, that you increase the rate of the neopentane a lot compared to palladium on a neutral support. So that will be the next one we'll look at. We'll look at the hydrogenolysis and neopentane, and the prediction is if there's electron donation to platinum, we expect the rate to be much higher than it is, say, on platinum on aluminum, platinum on silicon. We haven't done those experiments yet. So. Okay. Let me now turn to direct physical probes of the interaction. There are going to be three kinds of measurements we're going to make by X-ray absorption. They are the binding energy, the near edge structure, and the structure of the particle that one gets by X-axis. If you look at the so-called white line, or intensity right at the onset of photorejection of electrons, that is a qualitative nature of the density of electrons at the Fermi level. What's happening here, of course, is that we are varying the energy of the X-ray photon, and when we just get to this point where the cross-section is increasing, the so-called edge, we have just enough energy to photoeject an electron from a bound state, a core state, in the case of platinum, a P or an L state, to the continuum. But of course, right at the edge, it's not actually being above the vacuum level. It's a transition just to the Fermi level. And since the matrix element for that transition will be larger if there are lots of empty states there, then the intensity of the white line will be larger when there are lots of empty states. So if I really make lots of empty states, I go from the metal to the oxides, I get a huge effect. So here, the dark line, the full line, is platinum metal, and the blue line is platinum oxide. Well, I made a lot of empty states at Fermi level, and I got a big increase in intensity. So that is a qualitative measure of the density of states at the Fermi level. It's an electronic measure. Another bit of information we can get is the movement of this inflection point of the threshold, because that is a measure of the binding energy. And it has a distinct advantage over X-ray absorption spectroscopy, because that is limited to the outer few tens of angstroms of the particles because of the escape depth of electrons. So I really can't average over all the particles in the zeolite. Here, this doesn't rely on escape of electrons. The X-rays are very penetrating, so I can measure the binding energy over the average over all particles in the system. So that ought to be a better measure for binding energy for this purpose than XPS. But it's kind of difficult to do, because if you've ever done X-ray absorption spectroscopy, first of all, we have a huge number of values of our energy, 15.5 kilo electron volts, and we want to measure these energies to, let's say, a few tenths of electron volts. And these monochrometers have a lot of slack in them as you scan out and then mechanically come back and reset it. So the way you have to do it is you put two samples in parallel and have an internal reference. You measure the edge of the platinum foil at the same time as you're measuring the edge of your surface, and you internally reference it. You close down the slits so that the monochrometer resolution is something of the order of a half a volt to a volt. And in fact, you can then measure these binding energy shifts, or the inflection point edge shift, to about 2/10 of electron volt, which is about all people can do by ordinary X-ray microscopic spectroscopy. So we can get as much sensitivity as you can there. Now, I'll come back and interpret this a little later. I want to now just talk about this electron density at the Fermi level question. And the way I'm going to do it is, because they're rather subtle effects, I'm going to take a sample of the catalyst, and I'm going to line up the inflection point and subtract platinum from it, and only look at the difference spectrum. Okay, so right at the inflection point will be changes right at the Fermi level, and anything that happens elsewhere will be deeper down. And one of the things that one might expect is if benzene is more strongly absorbed than hydrogen, that if I put hydrogen on the platinum particle and then I saturate the hydrogen with benzene, the hydrogen ought to be displaced, and I ought to expect modest but measurable changes in the near edge structure due to some of the hydrogen or most of the hydrogen being replaced by benzene. So this is a different spectrum. It's the near edge spectrum of platinum on a magnesium L and hydrogen, from which the platinum foil measured simultaneously has been subtracted after you line the edges up. And you really can't interpret that different spectrum per se, but you can then go look and see what happens when you displace the hydrogen with benzene by saturating the hydrogen with benzene. And what you see is that there are changes right at the Fermi level, 0, where in fact when I go from hydrogen to benzene, I actually am filling up some state there. And the other changes you see are down here at about 11 or 12 volts below the Fermi level. Well, where is that? That's just the energy of the pi electrons of benzene. They're up about 10 volts from the Fermi level. So those are modifications that are happening in the pi orbital of the benzene. So this really does look like we have enough sensitivity to actually see these. Now, the really neat experiment, which we've tried but actually for a variety of reasons haven't got right yet, is to put benzene down and change it for toluene and see the electronic change there, where we ought to put more electrons in from toluene than we did to benzene. If you're interested in why we haven't got that right, discuss that question and answer. Fine. If we go now beyond the near edge and look at the x-apse, here's the K2 weighted x-apse function against in momentum space compared to our fit to that. Let me see, the points are the actual data and the solid line is the fit, and from this fit we can extract things like the Debye-Waller term and the coordination number and the energy to distance, and the numbers that we get out are that the platinum has essentially the bulk internuclear distance, 2.73 compared to bulk platinum foil of 2.746. Coordination number, of course, for the bulk is 12, and we get 6.8 here. If you turn that into a particle size, it's a particle on average of about 30 angstroms, or about 12 angstrom diameter. Now, that, if anything, is an upper limit, because we carefully tried to calcine and reduce these at low temperature to keep most of the platinum in the zeolite. But there's always a few particles which you see in the electron microscope that have come outside. And of course, if you average in the large particles which have a larger coordination with the small ones, because XAPS is a bulk technique that averages over everything. So this is an upper limit particle size. But it is about the right particle size if you think that what's happening is that these catalysts, which are prepared by ion exchange, grow until they sort of fill the cavity and then they stop. Because where they ought to stop is about 12 angstroms. This is one cavity in the parallel pore of the catalyst. Is this very small 6-membered ring, and this little small cage, and this one are the cancronoid cages. And the entrance in these undulating pores are about 7 angstroms, and the large pore here is about 12.6 angstroms. If you actually, there are 6 cation positions, of which 3 would be filled if it were a univalent cation that you had in there, and so that would decrease this size to about 10 angstroms. But in fact, this is a barium or magnesium, and what happens is, of course, for every barium or magnesium you put in, you take out 2 potassiums, and then when you calcine at high temperature, you move the cation out of the parallel channels into these cancronoid cages. So, in fact, on average, the catalyst, the cages have got to be somewhere between 10 and closer to 12 angstroms in diameter. So you could fit about a 12 angstrom particle in, which is what we see. But now, there's another thing about our catalysts that I need to tell you about. There seems to be 2 kinds, even when we try to make them more or less the same. Here, actually, I'm showing you some of very different loading, one which is a 1% loading and one is about 3.5% loading. They all have very high dispersions by hydrogen chemisorption. It, in fact, exceeds 1 somewhat for these low loadings, and it's about 1. But what's different is the way the CO chemisorption behaves. On some, it's very low. It's about a third of the hydrogen. And in others, it's about equal. Now, I have reason to believe that those catalysts that Amoco and Chevron make that they think are commercially interested are ones that are more like this. Though in a recent paper submitted from Amoco, they actually quoted our paper and said this was about right. I don't quite understand that. But what I think is happening here is these are catalysts that are made such that you're sort of blocking the ends of the pores, and the hydrogen can sort of chemisorb and move around the whole particle, but the CO can sort of only decorate that portion of the particle which hangs out of the pore. We wanted to try to look at how the dispersion was affected and the hydrogen to CO ratio was affected by calcination. We've been doing all of these at rather low calcination temperatures, 350 Celsius, and then reducing at the same temperature, primarily because we wanted to keep as much as we could of the platinum inside. But here's an example where it was ion exchange from the platinum amine to make about a 1% loading of platinum, and then it's back exchanged. The reason you back exchange this, if you ion exchange the platinum in, you've got a platinum 2+ cation, and then you reduce it. For every platinum cation in there, when you reduce it to metal, by stoichiometry, you have to put 2 protons somewhere. And so you actually build in acidity by the ion exchange reduction. So to get rid of that residual acidity, you back exchange after you reduce the metal, the protons for potassium, to get back to a more basic catalyst. And then what you're seeing here is the hydrogen to metal ratio after reduction, which the reduction was always done in this case at the same temperature, which I believe was 350. But the calcination was done at different temperatures, from 450 up to about 850. And you can see the dispersion goes to a maximum of about 1. The maximum dispersion occurs at somewhere in the order of 600 degrees Kelvin. Is that unique to the L zeolite? Well, apparently not. Somebody's, of course, done it for alumina, and it doesn't look all that different. Here's again, the dispersion as a function of calcination temperature. This is a 0.6% platinum on alumina, and it doesn't say what the reduction temperature is here, but I think it was about 500 degrees also. And again, what you see is that the dispersion maximizes somewhere in this range of 6 to 700 degrees Kelvin. For this whole sequence, actually, I'm only showing you one sequence. We did a whole bunch of these: barium exchange, potassium back exchange, impregnated ion exchange. A curious thing, normally if you're doing preparations of metals on silica or alumina or other supports, the conventional wisdom is if you want a higher dispersion, you ion exchange. If you do an impregnation, incipient wetness, something like that, you always get less good dispersion. But on these L zeolites, the dispersion is better for impregnation than ion exchange. This is another thing we don't understand and we're trying to understand. And so we did a lot of these, but I'll show you the results of this one sample. And in this case, same experiment, but now we're looking at the CO hydrogenation, sorry, the CO chemisorption as a function of calcination. And in this series, it looks like what I guess the industrial catalyst does, that the CO to hydrogen, the hydrogen-CO ratio is not a third, but it's more like 0.7. It's not much changed. Now, the question is, well, what is the correct measure of particle size? Is hydrogen chemisorption? Is CO? Would the real particle size stand up in this work? And so we went back to XAPS, and here there's a lot of data put together, but let me take you through it slowly. We have sort of three measures of dispersion, or particle size. If the rule of thumb is that if you take 1 over the diameter, sorry, 1 over the dispersion, you'll get the diameter in nanometers. Or if you take 1 over the dispersion, 10 over the dispersion, you'll get the approximate diameter in angstrom. And so 1 over the hydrogen dispersion says that the particle size goes from about 10 down to 9 up to 43. 1 over the CO gives you similar sort of behavior. The numbers are somewhat different, but here at this about 600 degrees calcination, we have a particle diameter which is of the order of 10 to 13, 10 to 14, however you want to read it, in the minimum size. And what we have over here is the XAPS coordination number. Now, turn coordination number into particle size. This is number of atoms, and this is the diameter, and there are two of them with an asterisk or two asterisks. And they're a slightly different calculation. In the first one, with one asterisk, you assume that the particles are formed with a face-centered cubic structure where you always put the nickel platinum closest to the center of mass, or another way of putting that, such that it has the highest coordination number. In the second one, with two asterisks, you take into account the interaction of the platinum particle with the oxide surface, and you try to minimize the overall energy. And that changes the number. These are the references where that has been done by this group in the University of Eindhoven. But you see, it's not a big difference, right? If we take this minimum particle size, it's 10 to 10.5 angstroms by XAPS, and by hydrogen it's of the order of 10, and by CO it's somewhat larger. So I guess that probably hydrogen chemisorption is not a bad measure. And the important point is that the qualitative result is the same. Whatever measure I use, the highest dispersion or minimum particle size occurs at the same point. So they're all telling me qualitative the same thing. And quantitatively, it's telling me that hydrogen's not a bad measure of particle size. It's about 10 angstroms in this particular preparation. Now I'm going to tell you the most surprising result that has to do with the metal-oxide interaction. Almost unbelievable, but of course we've reproduced it and you have to believe it. And that is that the particle seems to disorder or wet the surface when you take the hydrogen off it. And it's a reversible effect. This is just the Fourier transform of platinum foil as reference. This is the Fourier transform for these 10 or 12 angstrom particles when they're covered with hydrogen. Coordination number is 12. This is going to be something of the order of half that. That's what we see. And now what we do is we desorb the hydrogen. We take the hydrogen off by heating it up to about 270 and flowing helium, and then cool it back down to liquid nitrogen to get the XAF, and asks what happens. And what happens is the bare particle seems to just fall all over itself or fall apart. There are no platinum-platinum distances. Either it's enough disorder that we've lost the coherence that you need for the XAFs, or in fact it's actually spread out over the wall. That's very surprising because it's hard to understand it thermodynamically. What kind of interaction is there between the platinum and the wall that can overcome the platinum-platinum bonding? Either if you're going to disorder or if you're going to have it wet the walls. Either way, it's hard to understand. And yet, it's quite reproducible and in fact reversible. If you take these particles where there's no coherence, expose them to hydrogen at room temperature, you reform the particles and see it in the XAFs. Now, another possible explanation. Suppose that when we moved the hydrogen off, swept the hydrogen off at 270 degrees or whatever we used, I think it was 270 degrees with helium, we were careless, and we let in some oxygen. So that now it's disordered because we oxidized it. Well, first of all, we ought to have seen platinum-oxygen bonds, which we don't see. But now I go back to what I had shown you some time ago and say, well, there's another reason for believing that we have an oxidized D, and that's in the binding energy. Because if I oxidize something